Welcome back to the Bethany branch line. The last video introduced this elevator, and this time we're going to describe the control system for the elevator. This video shows the prototype and describes the logic. The next video will explain the parts and the wiring. A third video will explain the microcontroller coding. Now, let's take a look at the prototype. This is the system I devised for automatically controlling the elevator. The microcontroller is connected temporarily to a number of peripherals, and we'll explain them. Let's start by resetting the power to the microcontroller. The first thing that will happen in the startup procedure is the 4 gates will open for 5 seconds and then close. Okay, now it's operating, and the system is assuming that the elevator is between the 2 levels because neither the scenic switch nor parade switch are depressed by the elevator. We can show you what happens if I press the parade switch, representing the elevator at the bottom. The parade gates open, and the power is on for the elevator track and the parade level tracks, and off for the scenic tracks. And there's no error light on. When I release the parade switch, it goes back to the in-between mode, closes all of the gates, turns off the track powers, and leaves the actuator to operate between the tracks. When it gets to the scenic level, the scenic gates open, and the scenic leads are turned on, as well as the elevator power. There is one other aspect to this that I thought about, and that was when an elevator begins to move from a level and the system wants to close the tracks, what would happen if there was a train in the way, preventing the gates from closing? The system needs a way to detect that, and that's what these 4 infrared detectors are for. So let me simulate a train at the scenic level by holding down. You can see it trips the detectors to put the blockage in the way. And if I release the scenic switch, the error light comes on. The gates remain open, and the elevator and parade level tracks, but also the actuator, are off, preventing anything from being moved until the blockage has been removed. So now if I go ahead, as soon as I remove the blockage, the gates are going to close and the actuator power will come back on and the track powers will remain off. So as you can see, the gates close and the track power is off and the actuator power is back on. Update. I made the error mode more intrusive by adding a separate flashing LED. This concludes my presentation of the elevator prototype. Now I will explain the logic behind the elevator control system. I'm indebted to Rudy's hobby channel on YouTube for showing how to work out an electronics control system. Rudy is a great resource. A link to his channel is in the video description below. His series of videos on building a custom automatic crossing gate for his railroad simplifies the thought process. I adapted it for my logic system. The purpose of a logic system for electronics is to break down a complex process into manageable steps. So we start with the basic question, where is the elevator? And the elevator can be in one of three possible places: the parade level, between levels, or the scenic level. And each of those places represents a state that needs to be managed. So let's take a look at state 1, the parade level. The first step is to ask the question, have we already just been here? If the previous state is equal to 1, then we exit the parade level routine. But if not, we go ahead and handle the other steps. Raise parade gates, turn on the elevator track power, turn on the parade lead tracks, set the previous state variable to 1, and then go back to the start question, where is the elevator? So now let's take a look at state 2, between levels. So we start with the question, have we just been here? If we've just been in state 2, then we exit the routine. If not, we proceed with the other steps. We first turn all of the track powers off, the elevator track and the lead tracks for both the parade and scenic levels. And then we ask the question, are there any gates blocked? And if there is, if the sensor tells us there is, we turn on the error light and we turn off the power to the actuator so that the elevator can't move. And then we sit and wait for an all clear. And that would be accomplished by the train operator removing the trains that are following the gates. So when the operator sees the error light flashing, he or she will know to look for trains that are in the way of the gates at either the scenic or parade levels. If the all clear comes, then again, it loops back to the question, are there any gates blocked? And if not, then all of the gates at the parade and scenic levels would be lowered. The actuator power will be turned on, the error light will be turned off, and the previous state variable will be set to 2. And then we go back to the start question, where is the elevator? So now let's take a look at state 3, the scenic level. So it starts with a question, if previous state variable is 3, have we just been here? We exit the routine. If not, we go to the next steps. We raise the scenic gates. We turn on the elevator track power. We turn on the scenic lead tracks power, and we set the previous state variable to 3 and go back to the start. So this routine would then repeat over and over and over. One thing that is a physical reality is that if the train is at state 1 at the parade level, then it can only either remain at state 1 or proceed to state 2. It can't go directly to state 3, the scenic level. You have to be in between in order to get to the scenic level. So that concludes the explanation of logic. The next video in the series will describe the parts and the wiring for this project. So stay tuned to Bethany Branch Line, and thanks for watching.